let's move on. So what we're going to look at now is we're going to look at a particular type of study. In medical context, these are called case control studies. You will sometimes find that term used in management research. Sometimes they don't give it a special name. It's just an observational study where you take usually a sample of some sort, and you are looking at the relationship between two categorical values, each of which can have only two values itself. Okay, so the categorical values are an intervention of some sort, or a condition of some sort, and a control or a comparison. Okay, so that's the independent variable, and then the dependent variable is some kind of outcome, which is present or not present. Now the really famous big influential studies of this were the ones that related to lung cancer and smoking in the mainly in the 1950s and the 1960s.
Oh, Ed,
yeah.
Can you please just scroll down a bit I didn't get the last answer for the fourth one.
Oh, sorry. There you go.
Oh, sorry. Yeah, thank you.
Yep, got it. Yeah, so the big issue, this was a huge big deal back in the 50s and 60s, was, does smoking cause lung cancer? And of course, nobody was going to go and do an experiment where they got, thousands of people to smoke cigarettes for, 20 years, or not smoke cigarettes for 20 years, and then measure how many got lung cancer. The only way you could study it was in humans, was these retrospective studies and the way a case control study works is that you look at people, in that case you looked at people who got cancer, lung cancer, and you looked at people who didn't get lung cancer, and you looked to see whether they had smoked or not. And there were very, very big studies done of that, including a big study where the subjects were all doctors. There were plenty of doctors who smoked back in the day. So this is a really simple, in a way, it's a very simple research design. It's a very common one in academic research, but actually it comes up a lot when you get things like surveys. Okay, you get survey data, and this is a useful way to analyze certain types of survey questions. And that survey data is the kind of stuff that you're fairly likely to run into early in your career. So let's have a look at how this works. So just example here, let's say we have a representative sample of staff from a 24-hour IT support desk, and data about when people have taken sick leave. So we have two categories of staff here. We have people who work in the daytime, in one of the or both of the two daytime shifts, and people who work at night, who work in the evening shifts. There's two evening shifts. So the day is divided into four, let's say 6-hour shifts or something like that. And so what we're interested in, the independent variable, is whether a person works in a day shift or they work in an evening shift. We'll just assume that people either work in one or the other. And then the dependent variable is whether they actually turn up to work or not. Okay, whether they turn up to work, they attended work for what I'll call a shift slot, or whether they called in sick, they took sick leave for the slot. And so we present this in what's called a contingency table, and I'll explain some of the characteristics of that in a moment, but let's just make sure we're clear about the data. So there were 2021 day shifts. Okay, so that's this number here, 2021. That's 1932 plus 89, so 2021 day shift slots. So what I mean by that is, on a given day you've got 4 shifts. In a given shift you'll have a certain number of people working. They are working in what I'm calling shift slots. Okay, so each shift will have a number of slots which need to be filled by individual workers. Okay, so on that 2020, of those 2021 shift slots, most people turned up, filled their slot, did their job. 89 was sick and couldn't come in. And then for people in the evening shift, there were 1466 evening shift slots. 1,423 were able to come to work. 43 didn't come to work because they were sick. Okay, so that's all that means. We have totals down the bottom here. So over the period of the sample, there were 132 cases where somebody couldn't attend their shift slot, and 3,355 where they could, and altogether there were 3,487 shift slots. Okay, so that's the data. We often get data that can be put into this kind of contingency table format. It isn't always case control data, so you can get data from experiments that falls into this as well, but we're just going to concentrate on this type of study today. Okay, now, so the usual way of describing this, the sort of standard terminology, is the part I put in blue there in bold. That's called the contingency table, and really what you're interested in is the four numbers there. Then they're commonly printed with what are called margins. So the margins are just the totals. Usually when you have margins on a contingency table, the margins have the totals. There's some situations where you might put the averages, means or medians or something like that, but usually it's just the totals by default. Now there's a fairly common practice in terms of how you order things here, which I'm going to stick to. And so that is, when we look at something like this, we have in mind what we call successes and failures. Remember, we use that terminology in proportions when we're talking about proportions. So here, in the independent variable, what we're particularly interested in is the day shifts and sick leave. Okay, so we'll consider day shift to be the intervention, if you like, and evening shift to be the comparison, and then sick leave will be the success. Okay, that's the thing, the outcome that we're interested in, and attended work will be the failure. So remember that those words success and failure, they are just technical terms. They have nothing to do with whether something would be regarded as a success or failure in the real world. In real world, we'd probably regard somebody not turning up to work as being a failure, but that's not here. Okay. Now, we can make a calculation about odds from a contingency table like that. So let me just give you a little bit more terminology about contingency tables. So we've got the intervention and success, comparison, failure, and then by convention we label these four cells A, B, C, D in that order. Okay, and that's the common way that it's done. And so when people are describing formulas about 2x2 contingency tables, and let me tell you, whole books have been written about analysing 2x2 contingency tables. It's a big deal. They usually use this convention. So we can do a pretty simple calculation, which is just involves the diagonals. We multiply A by B and divide it by B multiplied by C. So that's this formula here. And that calculates something called the odds ratio. Okay, so we do it with our actual data. And now we get this result here, which is 1.52. Now, I've got a typo here, and it's good that it's there because it'll help me emphasize an important point, because I actually, I think I'm pretty sure I've changed it a little. I've quoted this again a bit later in the notes, and I've actually changed it. I'm pretty sure I've changed it later on. So strictly speaking, this is not true. We don't say most likely or more likely. What we really should say is the odds are 0.5 to greater. Okay, something like that. We'll look at this next week. We'll probably see an example where we are allowed to say more likely, but strictly speaking, even though it's commonly done, this is a little bit like the way you talk about confidence intervals. So strictly speaking, you shouldn't say more likely, but you'll often find that sort of thing said in research papers. Now, the thing about the odds ratio is you can calculate a confidence interval for it. So we'll get to that. Before I do that, I'm not going to go through it in detail, but this little multiplication across the diagonals is the quick way to get the odds ratio. Okay. The long way is to calculate the odds for shift workers and calculate the odds, for evening shift workers and day shift workers, calculate the odds of them taking a sick day and then dividing them. Okay, that involves quite a bit more calculation, but you do it all and you get the same result. And I've given you a link there to there's quite a good online calculator that's hosted by the Campbell Collaboration, which is a kind of evidence-based. It's a bit broader than management, but it's an organisation that promotes and sponsors evidence-based practice, I guess would be the way of putting it. So this will not only calculate the odds ratio for you, it'll calculate a confidence interval, a 95% confidence interval for the odds ratio. And I do later in the notes, I've got a section I call technical notes, which you don't have to read, but that includes the formula if you want to do it yourself. It's a bit more complicated than the confidence interval formulas that we've used to date. But you should calculate the odds ratio confidence interval if you're working with sample data. Now, the way that odds ratios work is that if the odds ratio is 1, in other words, if both cases have the same odds, then there's no difference. So what you're looking for when you look at a confidence interval, looking at a confidence interval for odds ratios, is if the confidence interval doesn't include 1, then you can make a claim about being 95% confident that there is a significant difference, statistically significant difference. Because in this case, let's look at the probabilities. Or look at the odds. Okay, so the odds there for the day workers are 0.046, and the probability is 0.044. Okay, that's tiny. Okay, it's a pretty tiny effect size, and same here. So even though it's statistically significant, it's not a very practically significant effect. So that's odds ratios. I've got some more examples later on, and we'll probably look at it again next week. But as I say, you will find they're used quite a lot, and there are many other important sort of data analysis procedures that use odds and odds ratios. So it's kind of worth getting used to the idea. Certainly, everyone should know what odds are and how to calculate them. And it's not a complicated formula at all. But odds ratios are one useful way of understanding what's going on in these observational case control type studies. Now, what I'd like to do is I'll just break from presenting for about 5 minutes and take questions, but you're welcome to go and get a cup of tea or something. But we'll resume at 5 o'clock.
Ed?
Yeah.
Yeah, I didn't get that formula from the first page. I think when you started talking about it, it's the one that was
Right up the top.
I think so. Yeah, that one. Sorry, just go down a bit. Yeah. Thank you. That one. Just one. Yep. Sorry. I just wanted to make sure. Right. Yeah, thank you.
That's all right. I mean, the way to remember it is if you remember that when you're dealing with something being true or not true or happening or not happening, there's only two possibilities there, and the probabilities have to add up to 1. Okay, so that's a law of probability. They have to add up to 1, and then if you know that, then if you know the probability of one of them, you can just work out by the probability of the other by subtracting it from 1. That's all you need to know about going from probabilities to odds. You need to know that fact, and then you need to remember that odds are just the probability of something happening divided by the probability of it not happening, or the probability of something being true divided by the probability of it not being true.
Mm-hmm. Okay.
Yep.
Thank you.
But as I said, I think when it comes to the Melbourne Cup in a few weeks, I think they use I can't remember now. Some of the ways that odds are quoted on gambling sites are very strange to non-gamblers like me. Or non-regular gamblers.
Why? What's the probability of winning the lotto?
What's the probability of winning the lotto? I don't know, but you can, what's the odds might be a question to ask. Well, let's say the probability is 1 in a million. Okay, that's probably a ballpark. Well, you mean winning the big prize, not winning.
Yeah, winning the big jackpot.
Okay, I don't know I forgot what the lotto's even called here. Is it Powerball or just Lotto? Or let's say it's 1 in a million. Okay, so it's 0.00. What's that? 100,000 0 0. Is that right? 10, 100,000, 10,000, 100,000. Yeah. Okay, so 1 in a million. So it's going to be that over whatever it is. I think I've got this right. 9, 9, 9, 9. Let me do the calculation. Okay. Well, it's 1,000,000 to 1, basically. What happens is when you get very small probabilities, when you're getting sort of less than 0.01 or something is your probability, the probability and odds are almost the same number.
Okay.
Yeah. So it's let's move on. Okay, so still sticking with this example, so our contingency table, we can actually, this is a case where we can actually calculate pretty easily a correlation coefficient. And the correlation coefficient, it's called the Phi correlation coefficient, or sometimes it's called Pearson's Phi correlation, because the same Pearson who invented the ever popular Pearson's correlation coefficient also invented this one. Now, so what the calculation involves is you've got the cell here, which we call A, and the cell D. So you multiply those by each other, the numbers, and then we've got B and C there, and you multiply B and C by each other, and you subtract that from A times D. And then what you do is you divide that by all of the row and the column totals all multiplied together, but you take the square root of it. So the formula looks like that. So that's just the Greek letter phi. Okay, so it's A times D minus B times C, and then you just multiply 2021 by 1466 by 3355 by 132. You find the square root of that, and that will give you an actual correlation coefficient. And just like the Pearson's correlation coefficient, it ranges from -1, meaning a negative correlation, to 1, and 0 means no relationship, no association. The interpretation of it, there's sort of different versions of this floating around, but I got this one from a fairly authoritative source. I mean, any of these sort of weak, median, strong type effect size things, they are matters of sort of judgment and convention. But for this one, phi less than 0.2 is a weak association, so we only got 0.04. That's a very weak association. 0.2, 0.6 moderate, and more than 0.6 strong. So it's slightly different to the Pearson's correlation one, but it's fairly similar. Okay, so that's kind of a handy thing to know. It's another way of reporting on the results of something like this. Very handy if you've got survey results and you've got this sort of data to work with. All right, let's just summarize this before we go on. So in a case control study, you're dealing with historical data. There are some different ways of dealing with it if you're doing, say, an experiment where you're setting things up in advance and measuring. Okay, so this is case control is when you're just dealing with historical data, or there are other names for it. So people call it observational data, they call it cross-sectional, and so on. The terminology actually is it's quite confusing, I have to say. But the clearest terminology seems to be from broadly the kind of medical domain. Now, so your data breaks down like this. In the case we've looked at, we've got a sample overall 3,487, and they can be divided into two subsets. There's an intervention group, that's the day group, the day shift group, and there's the control or comparison subset, and that's the evening shift workers. And then for each of those, they can be further divided into success, which in our case just means the thing we're interested in, the outcome, which is missing a shift because you're sick, and failure, which is actually turning up to work because you're not sick. Okay, so in each of those they can be subdivided again. So that's the structure that leads to a 2 by 2 contingency table. And then when we put it into the contingency table, it looks like this. So we the 4 numbers there in blue, A, B, C, D. That's the actual contingency table, and then from that we can calculate an odds ratio. And so it's just a very simple formula. We multiply that by that, and then we divide it by that multiplied by that. Okay. Or we can use an online calculator. And we can also get a 95% confidence interval, but you're either going to have to use a formula, which I don't expect you to know, or I think if most calculators that do this online, there's plenty of them, will probably give you the confidence interval. And then we can also calculate a correlation coefficient, which we call Phi, and that again is not a particularly difficult calculation. So it's A times D minus B times C. So it's the top of that one minus the bottom of that one, and then it's divided by the square root of the product of the row and column totals. I won't really go through the little technical notes here, but quite a few people in the class have done statistics courses, so they will have learned something called the chi-squared test. And Phi, for 2 by 2 contingency tables, you can do a calculation to get Phi from the chi-squared statistic. It's also very closely related to Pearson's correlation coefficient. It's mathematically more or less the same. And there's another one that people learn about, which is called Cramer's V, and it's the same thing as Cramer's V for a 2 by 2 contingency table. And then this is the horrible formula for working out the confidence interval, which I've put here in proper mathematical notation. Okay, so that's just a bit of technical background. Next week I'll actually show you yet another way to look at these, which is using proportions, but we won't worry about that now. Okay, let's do a practice example. So similar sort of thing. This is a survey example. Okay, so 738 uni students complete a survey. One of the questions: do you own an electric scooter? So the sample here divides into two subsets. There's master's students and undergraduate students. And we'll say that we'll treat the master's students as our intervention, if you like, our sort of case of interest, and the undergraduates as the comparison group. So 56 said owned their own scooter, and the remainder said they didn't. And then with the undergraduates, there were 408 undergraduates. 18 said they owned their own scooter, and the remainder said they didn't. Is there a significant difference between the chances of a master's student owning an electric scooter and those of an undergraduate student? And then how big is the effect? All right, let's. So what we need to do here is we need to start by drawing a contingency table. It might be, well, I'm not the greatest at drawing on screen, but I'll do my best. Okay, so we know let's see if I can not make a total mess of this. Okay, we need 1, 2, 3. Okay. I'm doing this right. Okay. So we'll say we've got master's students, undergraduate students, and then I'll put an O there for own an electric scooter, and an N. I'll put N for not own. Okay. So owning an electric scooter is our success. Not owning one is the failure. Masters is the intervention group, the focal group, and undergraduates U is the comparison group. So what do we know? We know there were 330 master's students, and we know there were 408 undergraduates. And we know there were 56 successes with the masters, so 56 master's students had a scooter, and what was it, 18 undergraduates. Okay, so I'm going to need another row on my very shaky looking table here. There we go. All right, so I'll just get my calculator out and work out some totals. Okay, so we got 330. Okay, so we've got 274 master's students there that don't have scooters, and we have 390 I've actually made a mess of that. It's not right at all. That should be 18 there. That's 18. And that's going to be 400, and that's going to be 390. 390, yeah. Okay. All right. And then we can add up some totals here.
74.
74, good, thank you.
Next one, 664.
Sorry?
664 is the next one.
664.
And then 738. Yeah.
Okay, beautiful. Thank you for that. Okay, so there's our contingency table. So we'll start off with the odds ratio. Now, so that's going to be, we'll call that OR. So that's going to be 56 times 390 over 18 times 274. Okay. Okay, so I get 4.23. Sorry, 4.43 there. Does that sound right? Now, has anyone done that with the calculator, the online calculator? Let me get the link up. Where is it? 56, 274, 18, and 390. Okay. All right, so we get 4.3, and then this gives us a 95% confidence interval, which is, say, 2.55 to 7.70. Okay. Right, so that's how you do that. So what we can say there is that that being a master's student significantly increases the likelihood that you will own an electric scooter. It more than doubles the odds. Okay. Now, so that's one way. That gives you some idea of the effect. But the other way is to express it as a correlation. So to do that, we're going to be doing that diagonal multiplication thing, and then dividing by the square root of. Whoop, what happened there? That's me. Sorry. I don't know where that even came from. Okay. All right, so this is going to be a little bit of a, this is going to be 56, oops. Okay. Try again. 56 times 390 minus 274 times 18, all of that over the square root of 330 times 408 times 664 times 74. Okay, I'll wait for somebody to tell me the answer to that.
I got 0.208.
Sounds right. Okay, so we'll say 0.21. So based on those effect size numbers up here, that's just over the line to be a moderate association between say master's level enrollment and electric scooter ownership. Okay. So that's there are a couple of quite useful techniques, particularly I think in management. You know, a very common application of those is going to be dealing with various kinds of survey results, not particularly demanding in terms of the nature of the data itself, and you know this this confidence interval is a bit hairy to calculate by hand, but as I said, there's you shouldn't have too much trouble finding an online calculator that will do that for you. Now, so that's that one. Let's now move on to Bayes' rule.